Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stacks series.
It's wonderful to be back. I'm really looking forward to this one.
Today, we are exploring ancient engineering marvels, the science of longevity and resilience. And I have to be honest, when I started going through the research for our conversation today, I had this preconception. I think most of us do.
Oh, I know exactly what you're going to say.
We see history as this, this perfectly straight upward line.
Right. Old means primitive, new means advanced.
Exactly. We have smartphones, they had chisels, so we must be smarter. End of story.
It's what some call the chronological arrogance of our age. We just assume progress is this neat linear path. But when you actually dig into the material science, really get down to the chemistry and the physics of what the Romans or the Incas or the ancient Chinese were doing, that straight line starts to look, well, a lot more like a jagged curve.
Oh yeah. In some very specific, very important areas, we are, and I mean this seriously, we are only just now catching up to where they were 2,000 years ago.
Okay, that's a pretty bold claim. You're saying we, with all our modern technology, are catching up to people who didn't even have electricity.
In terms of sheer durability and resilience, absolutely. Think about it. We build a modern concrete pier, and we're happy if it lasts 50, maybe 100 years before it starts degrading.
Right.
The Romans built harbor structures that have been sitting in corrosive salt water for 2 millennia. And they're not weaker. They are measurably stronger today than the day they were first poured.
And it's not just the Romans.
Not at all. We build these massive ecosystem-destroying dams to control rivers. In 256 BC, the Chinese built an irrigation system that uses no dam at all.
The Zhejiang system.
Yes. It regulates itself using nothing but natural physics, and it's still irrigating the Chengdu Plain right now as we speak.
So the mission today is to go beyond just looking at these things as, pretty ruins or tourist attractions. We're not just here to say, wow, the Pantheon is big.
Exactly. We want to understand the how. We want to break down the chemical formulas, the fluid dynamics, the seismic physics that let these ancient structures basically defy time.
Okay, so let's lay out the roadmap. Where are we starting?
We'll start with the foundations. This is what we think we know. We'll look at the Pantheon, that Zhejiang system, Mayan water management, and the incredible seismic design of the Incas.
And then
we get into the active debate. This is where the science is really exciting. The new studies, like one from MIT in 2023, that have just completely flipped our understanding of things like Roman concrete.
Okay, and after that, we look forward.
Right, to the frontiers. How can we actually use this ancient knowledge to solve very modern problems, like climate change and sustainable infrastructure?
And finally, we'll wrap up with the implications, the big questions. What does it mean for a society to build for eternity versus, say, building for the next fiscal quarter?
It's a real collision of archaeology, chemistry, engineering, and even philosophy.
I love it. Let's jump in. Let's start with the big one, the one everyone knows. The Pantheon in Rome.
The heavy hitter, completed around 126 AD.
Under the Emperor Hadrian.
That's right. The inscription on the front credits Marcus Agrippa, which confused historians for centuries. But yes, the massive dome we see today is absolutely Hadrian's beast.
And it is the world's largest unreinforced concrete dome. I want to linger on that word, unreinforced.
It's the whole story.
Because anyone in construction today knows the deal with concrete. It's fantastic under compression. You can pile weight on it all day.
But it's terrible under tension.
Awful. If you pull it or bend it, it just snaps. That's why we fill all our modern concrete with a web of steel rebar.
The steel handles the tensile forces. The concrete handles the compression. It's a composite material.
But the Pantheon has no steel.
Zero. Not a bit.
So just from a pure physics standpoint, a dome that is 43 meters across, that's 142 feet made of what we think of as brittle concrete, it just shouldn't be standing.
It really shouldn't. The outward thrust at the base, what engineers call hoop stress, should have cracked it open like an eggshell thousands of years ago.
So the big question is, why is it still there?
And that is the question that has obsessed architects and engineers ever since the Renaissance. The answer is that the Pantheon isn't just one type of concrete. It is an incredibly sophisticated, layered system of different concretes. It's a masterpiece of density management.
Okay, so think of it like a layer cake.
A very, very carefully engineered layer cake, where each layer has a different recipe and a different weight.
Right, break it down for us. I'm a Roman builder in 126 AD. What am I pouring for the foundations?
At the bottom, you need mass.
Yeah.
You need sheer weight to anchor this thing and resist that outward push we talked about.
But you want the heavy stuff.
The heaviest stuff you could find. So the concrete mix for the foundations and the thick drum walls at the base is filled with heavy aggregates. They used huge chunks of dense travertine and basalt.
Basalt, that's the dark, heavy volcanic rock, right?
Yeah, very heavy. The density of the concrete at the base is around 2,200 kilograms per cubic meter. It's basically man-made rock. But, and this is the key, you can't keep using that heavy mix all the way up.
Why not?
The dome would be too heavy to support its own weight. The walls would literally be crushed from above. It would collapse before you even finished it.
So they had to lighten the load as they went up.
Systematically, it was all planned. As the walls rise higher, they switch the aggregate in the mix. They stop using the heavy basalt and start using crushed terracotta tiles and lighter tufa limestone. The density starts to drop.
And by the time they get to the dome itself.
The mix changes again.
Yeah.
But for the very top section, the final ring around the central opening, they switch to pumice.
Pumice. Wait, that's the volcanic rock that's so light it actually floats on water.
That's the one. They quarried porous volcanic pumice, hauled it all the way to the construction site, crushed it, and mixed it into the concrete for the apex of the dome.
That's incredible.
So the density at the very top is only about 350 kilograms per cubic meter. That is almost half the weight of the concrete at the bottom.
They literally engineered the weight out of the building as they built it.
They did. If they had used that heavy basalt mix at the top, the physics just wouldn't work. The tensile stress would have been far too high, and boom, it would have failed.
The logistics of that alone are staggering. You know, no trucks, no modern cranes. They had to source these specific types of rock, keep them all separate on site, mix them in precise batches.
And then haul them up and pour them at the exact right elevation. It implies a supply chain and a level of project management that honestly rivals anything we do today.
But you're saying the materials are only half the story. The other half is the geometry.
The geometry is the other half, yes. And we have to talk about the oculus, that giant hole in the center of the roof.
The Great Eye. It's about 8 meters, 27 feet wide?
Right. And most people just assume it's for light, or maybe it functions as a giant sundial, and it does those things. But from a structural point of view, it is an absolute stroke of genius.
Why?
In any dome or arch, the most structurally problematic part is the very top, the apex. It's where the keystone would be. It's under immense compressive force, and it's usually the heaviest single point.
And the flattest part, too, so gravity's pulling straight down on it.
Precisely. The Romans looked at that problem, and what did?
They just deleted it.
They just got rid of it. They removed the single heaviest, most structurally dangerous part of the entire roof. But they didn't just leave a hole. They reinforced the edge of the oculus with a massive compression ring made of brick, which takes all those forces and directs them downwards and outwards into the ribs of the dome.
Speaking of ribs, let's talk about the coffers. Those square, sunken panels you see all over the ceiling. They look decorative, but I'm guessing they're not just for looks.
They are pure engineering. If you go into a modern parking garage, you'll sometimes see what's called a waffle slab ceiling.
Right, a grid pattern.
It's a grid. The concrete is thick in the ribs of the grid, where you need strength, and it's thin in the middle of the squares to save weight. The Romans invented that 2,000 years ago.
So by scooping out those squares, the coffers, they're just removing dead weight.
Tons and tons of it. They carved out all the concrete where it wasn't structurally necessary, leaving behind only the grid of ribs to carry the load. It's a classic optimization problem. Maximize stiffness while minimizing mass. And they solved it without a single computer.
It's humbling. I want to shift gears, though, because we're talking about controlling solid forces like gravity, but there's another force that is much, much harder to control.
Water.
Water, it's relentless, it floods, it erodes, it carves new paths, and usually when we want to control a river, we build a dam.
We build a giant wall of concrete, the brute force approach.
We just say, stop. But in China, around 256 BC, so this is predating the Pantheon by nearly 400 years, a local governor named Li Bing looked at the Minjiang River, which was constantly flooding the Chengdu region.
A classic flood drought cycle. Too much water in the summer, not enough in the winter.
Right. And he decided to fix it, but he didn't build a dam.
And that's what makes the Zhejiang irrigation system so remarkable. It's the only major ancient irrigation system on Earth that is still functioning today, and it works without a dam. The reason is that Li Bing didn't try to conquer the river, he decided to guide it. He used the river's own physics against itself.
So paint the picture for us. If there's no big wall, what's there?
The system is a machine made of 3 main parts that work in harmony. The first is called the Yuzui, which translates to the fish mouth.
The fish mouth.
It's a man-made levee, an embankment built right down the middle of the river, shaped like a long, curved fish. And its job is to split the river in two.
Like a fork in the road.
Exactly. It divides the river into an inner river, which goes toward the irrigation canals to the farms, and an outer river, which is the main original riverbed.
Okay, so it's a 50-50 split.
Ah, no. And this is the genius part. It's a dynamic split that uses the river's own topography. In the low water seasons, winter and spring, when the farmers need water most, the deeper channel on the inside curve naturally directs about 60% of the river's flow into the inner river, to the farms.
So it prioritizes irrigation when water is scarce. Makes sense.
But then the summer monsoons hit, the water level rises dramatically, and the physics of the flow change. The floodwater is faster and deeper, and the centrifugal force caused by the bend in the river pushes the bulk of that fast-moving water towards the outer river.
So the ratio flips.
The ratio flips automatically. In flood season, 60% or more of the water is diverted away from the farms and safely down the main riverbed, protecting the entire plain from flooding.
Wait, hold on a second. This whole switching mechanism, it's automatic. There are no gates to open and close. No one is operating it.
No gates, no sensors, no computers, no human intervention whatsoever. It is purely hydraulic geometry. The shape of the channel itself dictates where the water goes based on the volume and velocity of the flow. It's a passive, self-regulating system.
That's incredible. But rivers don't just carry water. They carry silt, ton of silt, sand, rocks, mud.
A huge problem for any irrigation system.
Right. If you divert river water into a canal, that canal usually clogs up with sediment in just a few years. How did Li Bing solve the silt problem?
That's the second component. The Cheyenne, or the flying sand sluice. And to get this, you have to understand the physics of a river bend. When water goes around a curve, it creates a vortex, a secondary flow. The water on the surface gets pushed to the outside of the curve, but the water along the bottom, where the heavy sediment is, gets pulled toward the inside.
Okay, I think I'm picturing that.
So Li Bing knew this. He built the intake for the irrigation canal on the inside of the curve where the water is cleaner, but he built a low spillway, the flying sand sluice, on the outside of the curve.
So the vortex flow happens, the heavy rocks and sand get swept to the outside of the curve,
And they get flung over the spillway. The hydraulic force literally throws the sediment over the wall and back into the main outer river, keeping the irrigation channel almost perfectly clean.
So flying sand isn't just a poetic name.
It's a literal description of the physics at work. It automatically removes about 90% of the sediment before it can even enter the irrigation system.
Unbelievable. What's the third piece?
The third piece is the beopinku, or the bottleneck. This was the hardest part. His engineers, led by his son, actually carved a narrow channel straight through a mountain, Mount Yule. This channel acts as the final throttle,
A choke point.
a natural check valve. It's a fixed size. So no matter how high the river floods, physics dictates that only a certain volume of water can pass through that narrow opening at any given time. It physically prevents the entire Chengdu Plain from being overwhelmed.
The fish mouth splits it, the flying sand sluice cleans it, and the bottleneck regulates it.
That's it. And that three-part system has kept that region fertile and flood-free for more than 2,200 years.
It's just humbling. Today, our solution would be a multi-billion-dollar concrete dam and a fleet of dredging machines working year-round.
And they would be fighting the river every step of the way. Li Bing understood that it was easier to let the river do the work for you.
Let's travel now from a place that learned to manage too much water to a place that had almost none, at least on the surface, the Maya civilization.
The Maya are a fascinating paradox in engineering. We see these incredible stone cities, Tikal, Palenque, deep in what looks like a lush rainforest. So you assume, oh, it's wet, there's water everywhere.
Except that's not the case.
Not at all. Geologically, the Yucatan Peninsula is a nightmare for a large civilization. It's what's known as karst terrain.
Which means it's basically a giant limestone shelf.
A giant stone sponge. Limestone is incredibly porous, full of cracks and fissures. So when it rains, and it rains torrentially in the wet season, the water doesn't pool on the surface to form rivers or lakes.
It just vanishes.
It vanishes. It seeps straight down through the rock into deep underground cave systems and aquifers. There are almost no surface rivers near the major Mayan sites.
So you have a civilization of millions of people living on a sponge, and to make matters worse, they have a brutal dry season that can last 4 to 6 months.
Exactly. If you can't capture and store the rain when it falls, your city dies. So the Maya had to do something radical. They had to turn their entire cities into massive water catchment systems.
The architecture itself was the infrastructure.
That's the key insight we're getting from modern archaeology. The pyramids, the plazas, the roads, they weren't just ceremonial or functional in the way we think. They were all part of a giant funnel.
How so?
The grand public plazas were meticulously graded and paved with plaster to be waterproof. The Sac Beeb, the famous Mayan roads, were raised and sloped to act as channels. Temple roofs were designed with gutters. Everything was engineered to capture every single drop of rain and funnel it towards massive man-made reservoirs.
And these weren't just muddy ponds.
Oh no, if you just dig a hole in limestone, the water just leaks out the bottom. They had to waterproof them. And this shows their incredible knowledge of local geology. They would find and sometimes import specific types of clay from miles away, clays that were chemically perfect for creating a seal, and they'd line the reservoirs with layers of this clay and plaster.
We're talking about a huge scale here. How much water could they store?
At Tikal, which was one of the largest cities, archaeologists estimate the reservoir system could hold around 40 million gallons of water.
40 million.
Enough to sustain a population of tens of thousands of people through even a prolonged drought.
But they weren't just storing static water. I was reading about Palenque, where they found evidence of something that looks a lot like a pressurized water system.
Palenque's a different case. It's in the highlands, so they had actually had springs and small streams. Their problem was too much water flowing through the city center.
So they channeled it.
They built sophisticated underground aqueducts to divert these streams safely under the plazas and buildings. But in one of these aqueducts, archaeologists found a section where the channel narrows abruptly. It goes from a large cross-section to a much smaller one.
And according to Bernoulli's principle from physics, if you force the same amount of fluid through a smaller area, you increase its velocity and pressure.
You've got it. They were creating what's called a hydraulic head. The calculation suggests this system could have generated enough pressure to shoot a jet of water about 6 meters or 20 feet into the air.
So they had fountains.
Fountains for aesthetic or ceremonial purposes are the leading theory, or maybe even a system for flushing waste. But the very idea that the Maya were manipulating water pressure, something we usually associate with Roman or even modern engineering, it's just astounding.
So we've covered gravity, rivers, and rain. Let's wrap up our foundation section with the earth itself, the Incas. They built their empire in the Andes, which is basically, what, a seismic mosh pit?
That's a good way to put it. It's right on the Ring of Fire. The Nazca tectonic plate is actively grinding underneath the South American plate. Earthquakes are not a rare event. They are a constant fact of life.
And yet their structures survived.
Better than the ones that came after. When the Spanish conquistadors arrived, they often tore down Inca temples and built their own churches on top of the original Inca foundations. And when the big earthquakes hit over the centuries, the rigid Spanish churches would collapse into rubble. But the Inca walls underneath them would remain standing.
Because of the famous perfect fit stones, the ashlar masonry.
It's the hallmark of their imperial architecture. These massive, multi-ton granite blocks cut into complex, irregular polygons that interlock with breathtaking precision.
And the key is no mortar, not a drop of cement.
You can't fit a knife blade between the stones. And I've always been fascinated by that no mortar rule. Intuitively, you'd think gluing the rocks together would make the wall stronger, right?
It seems like it should.
In a world without earthquakes, maybe. But in a seismic zone, rigidity is your enemy. If you cement blocks together into one solid, rigid unit, when the seismic wave hits, that rigid unit has to absorb all the energy. And it snaps. It cracks and shatters.
So the Incas understood that flexibility was the key.
They did. Whether through centuries of trial and error or pure genius, they understood that the structure needed to dissipate the earthquake's energy, not resist it.
And the lack of mortar lets the stones move.
That's exactly it. It's a phenomenon engineers now call seismic dancing. During an earthquake, the individual stones in an Inca wall are free to vibrate and move slightly. They rattle against each other.
And that movement, that friction, dissipates the energy.
It converts the violent kinetic energy of the earthquake into harmless heat through friction. The stones literally dance in place, and because of those complex interlocking shapes, they can't fall out of alignment. When the shaking stops, gravity just settles them right back into their perfect original positions.
The wall is basically a giant, heavy shock absorber.
It is. And it's not just the joints, it's the overall geometry too. Look at any Inca door or window. It's not a rectangle, it's a trapezoid. It's narrower at the top than it is at the bottom.
Why does that shape help?
Stability. A trapezoid has a much lower center of gravity than a rectangle of the same height. And on top of that, the walls themselves are battered. They lean inward at a slight angle, maybe 3 to 5 degrees.
So they're leaning into themselves.
Right. It creates a state of constant compression. The whole structure is pushing inward on itself, which makes it incredibly stable and resistant to the tipping forces of an earthquake.
Okay, so we've established these 4 pillars of just incredible ancient ingenuity. But this is where we need to shift gears a bit.
Into the active debate.
Exactly. Because for a long time, modern science looked at all this and we said, wow, they were amazing craftsmen, incredible stonemasons. But we didn't really think of them as chemists or material scientists.
We basically thought they were brilliant, but lucky.
Right. But now we're moving into this active debate section because a wave of recent studies, some as recent as last year, are proving that we were just completely wrong. The Romans, in particular, weren't just stacking rocks, they were performing high-temperature chemistry.
This is the story of the lime clasts. And this, for me, is where the whole narrative just changes. For decades, whenever scientists look at a cross-section of Roman concrete, they saw these little white chunks scattered throughout. Millimeter-scale white lumps.
And for years, the standard explanation was basically the Romans were sloppy.
That's it. The consensus was that these were just poorly mixed clumps of lime. They thought the Roman mixers didn't grind the lime powder fine enough or didn't mix it long enough. It was written off as a defect, a sign of poor quality control.
But a team at MIT, led by Admira Mathic, decided to take a closer look.
They did, in 2023. And they didn't just look with a microscope. They used high-resolution, multi-scale imaging and chemical mapping technologies. And they realized 2 things. First, these white chunks weren't a bug. They were a feature. They were present in all the most durable samples of Roman concrete. And that led them to question the entire recipe.
Okay, so let's walk through the normal way to make concrete. You take limestone, you burn it in a kiln to make quicklime, and then, and this is the key part, you slake it. You add water to it to create a safe, stable paste before you mix it with sand and aggregate.
That is the standard, safe, cool temperature method we've used for centuries. But Mathic's team proposed a radical new theory, that the Romans were doing something they called hot mixing.
Hot mixing.
They weren't slaking the lime first. They were taking the highly reactive quicklime, the calcium oxide powder, and adding it directly to the mix along with the volcanic ash and water.
And when you add water directly to raw quicklime,
you get a violent exothermic reaction. It explodes with heat. The internal temperature of the concrete mixture could have shot up to over 200 degrees Celsius.
So they were essentially cooking the concrete from the inside out.
Precisely. And this intense heat does 2 crucial things. First, it enables chemical reactions that just can't happen at room temperature, creating a more durable material. But second, and this is the big reveal, it creates those little white chunks. The heat prevents the lime from fully dissolving right away, leaving behind these brittle pockets of calcium, the lime clasts.
And these clasts are the key to the famous self-healing ability. Break that mechanism down for us.
So all concrete eventually gets tiny cracks. It's just what it does. In Roman concrete, when a microcrack forms, it eventually spreads until it hits one of these lime clasts.
Okay.
Now, normally, water getting into a crack is the beginning of the end, but here, it's the beginning of the repair. When rainwater or seawater seeps into the crack, it reacts with the highly soluble calcium in the lime clast. It dissolves it, creating a calcium-saturated solution.
Right.
As that solution flows through the tiny crack, it reacts with the other chemicals and recrystallizes as solid calcium carbonate, effectively gluing the crack shut from the inside.
It's like the concrete has its own integrated repair system, a built-in glue gun.
It's a perfect description. The MIT team actually proved this in the lab. They made 2 concrete samples, one with the Roman hot mix recipe, complete with line clasts, and one without. They deliberately cracked both of them and then trickled water through the cracks.
And what happened?
The modern-style mix just stayed cracked. The Roman sample sealed itself completely solid within 2 weeks.
That is... It's just mind-blowing. It's nanotechnology 2,000 years before we had a word for it. And it explains why structures like the Pantheon are still standing. They've been repairing their own age-related cracks for millennia.
And it gets even wilder when you look at the concrete they put in the ocean. The marine concrete.
Right. The seawalls and harbor piers.
For those, they used a very specific type of volcanic ash from the region around Naples called pozzolana. And what they didn't know, but what we now do, is that when this specific ash interacts with lime and the chemicals in seawater, it triggers a unique chemical reaction.
And this reaction forms a mineral called Al-tobermorite.
Tobermorite. It sounds like something out of a comic book.
And it kind of acts like it.
It does. These are rare, long, plate-like crystals that actually grow inside the pores and cracks of the concrete over time. They interlock like microscopic armor plates. And the craziest thing is, this reaction requires seawater to happen.
So modern concrete rots in the ocean.
It corrodes. The chloride ions in salt water attack the steel rebar and break down the cement paste. Roman marine concrete feeds on the seawater. The longer it sits in the ocean, the more these tobermorite crystals grow, and the harder and more durable it gets.
So for Roman concrete, time is an ally, not an enemy.
It's a material designed to be in a constant, open chemical exchange with its environment, and to use that exchange become stronger. It's a completely different philosophy of material science.
I want to touch on one more of these secret ingredient stories from the active debate section. We talked about Chinese engineering with Du Jiangyan, but they also had a secret ingredient for the mortar they used in things like the Great Wall and major tombs.
Ah, yes. The sticky rice mortar.
It sounds like a myth, but it's real.
Oh, it's absolutely real. Chemical analysis has confirmed it. About 1,500 years ago, during the Ming Dynasty and earlier, Chinese builders started mixing the soup made from boiling glutinous rice into their standard slate lime mortar.
Why on earth would they add rice soup?
Starch. Specifically, a complex carbohydrate polymer called amylopectin. It turns out that when you introduce this organic molecule into the inorganic lime mixture, it acts as a crystal growth inhibitor.
Inhibitor sounds like a bad thing, like it stops it from working.
It's the opposite. It doesn't stop the calcium carbonate crystals from forming. It controls how they form. It prevents them from growing too large and randomly, and instead forces them into a much more compact, dense, interlocking microstructure.
So it makes the final product stronger.
Incredibly strong and highly water resistant. There are historical accounts and even modern tests showing that walls built with this mortar could resist modern bulldozers and have survived magnitude 7.5 earthquakes. It's a brilliant early example of an organic-inorganic composite material.
But not all these ancient engineering stories have a perfectly happy ending. We have to talk about the dark side of this, specifically the Mayan collapse.
Yes.
We praise their incredible water reservoirs, but there's a very compelling theory that the very engineering that allowed their cities to thrive may have also contributed to their downfall.
This is the cautionary tale in the science of longevity. To make all of that beautiful, essential lime plaster, to waterproof the reservoirs, to pave the plazas, to stucco the pyramids, you need quicklime.
And as we just discussed with the Romans, to get quicklime, you have to burn limestone in a kiln at very high temperatures.
And your fuel for those kilns in the middle of the jungle is wood.
Huge amounts of wood.
Staggering amounts. Modern estimates suggest that to produce the plaster for just 1 single square meter of a temple's facade, you might have needed to burn as many as 20 large, mature trees.
20 trees for 1 square meter.
The scale of the deforestation was likely catastrophic. As the great Mayan cities grew, they clear-cut the surrounding jungle to fuel their lime plaster industry. But when you cut down a rainforest, you're not just removing trees, you're altering the local climate.
You change the whole ecosystem.
You increase the ground temperature. You reduce humidity and rainfall. You cause massive soil erosion.
So they created a man-made drought.
They likely exacerbated the natural cycles of drought that were already common in that region. The very engineering that allowed them to survive the dry season, the plastered reservoirs, required a material whose production made the dry season longer and more severe. It was a terrifying feedback loop. They basically engineered themselves into an ecological dead end.
That is a chilling lesson. And it brings us perfectly into our frontiers section, because we're looking at all this incredible ancient tech, and we have to ask the big question. Now what? What do we do with this knowledge?
Right.
We're obviously not going to start burning down forests for plaster again, but that self-healing concrete, that seems like something we could really use right now.
Absolutely. The modern cement industry is responsible for something like 8% of all global CO2 emissions. It is a massive polluter. And a big reason for that is that we just have to keep making more and more of it because our infrastructure crumbles after 50 or 70 years.
So if we could revive the Roman hot mix method.
If we can successfully commercialize that self-healing chemistry, and believe me, companies are racing to do this right now using that MIT research, we could potentially double or triple the lifespan of our infrastructure. If a bridge lasts 150 years instead of 50, you have drastically reduced the long-term carbon footprint of that bridge.
And we don't need to import special volcanic ash from Naples, presumably.
No, we can use industrial waste products like coal fly ash, which has very similar chemical properties. It's about replicating the chemistry, not the exact ancient ingredients.
And what about the Zhejiangyan model? Is there a frontier for damless water management?
There's a huge movement in modern civil engineering right now, sometimes called metabolic engineering or nature-based solutions. We're finally starting to realize that our rigid brute force control of nature often fails spectacularly.
So we're looking for more flexible solutions.
Exactly. We're looking at flood control systems that use the Zhejiangyan principle. Guide the water, don't just block it. Allow rivers to flood into designated restored floodplains rather than trying to wall them off completely. It's a more resilient approach.
It's less man versus nature and more.
More man working with nature.
Or, as you said earlier, dancing with it, like the Inca stones.
Exactly like the Inca stones.
And new technology is also changing how we even find these ancient marvels. You mentioned LiDAR.
Light detection and ranging. It's a game changer. Flying a plane over the jungle and using LiDAR is like having a digital machete that strips away all the trees and vegetation. It has completely revolutionized archaeology in places like the Amazon and the Mayan heartland.
We're finding cities that are bigger than we thought.
10 times bigger in some cases. We're finding vast networks of canals, farms, and highways that were totally invisible from the ground. It proves that the scale of their water engineering and their social organization was even more sophisticated than we ever dared to imagine.
It just makes you wonder what else is still hidden under the canopy.
Or under the ground. At places like Machu Picchu, they're using ground-penetrating radar and are finding that the old saying is true. 60% of the Inca engineering is underground in the form of deep foundations and complex drainage channels.
So we've looked at the past, we've debated the science, we've looked to the future. Let's bring it all home with the implications. Why does any of this matter to someone listening to this right now?
I think on the most profound level, it challenges our entire economic philosophy. We live in a society that is, in many ways, built on planned obsolescence. We design products and even buildings to have a limited lifespan.
It keeps the economy moving.
It keeps GDP growing, sure. We build things to be cheap up front, knowing full well we'll have to pay to repair or replace them in a few decades. It's incredibly resource inefficient.
The Romans and the Incas, they were running a different calculation.
A completely different one. They practiced a philosophy of high upfront investment for near-zero maintenance. They poured immense resources and energy into the initial build to ensure that the structure would endure for centuries with minimal upkeep.
Imagine if our roads were built like that. No more fixing potholes every single spring.
But that road might cost 5 or 10 times as much to build in the first place. It's a trade-off. But as raw materials become scarcer and the cost of carbon gets higher, that ancient build it once, build it to last forever model might start to look a lot more economically viable.
There's also the implication for resilience in the face of climate change. We're entering an era of increasing volatility, bigger storms, higher floods, more extreme weather.
And our rigid, brittle infrastructure is snapping under the pressure. We build a concrete seawall, and a more powerful hurricane comes along and just breaks it. We need to learn the lesson of the Inca walls and the Roman concrete.
That resilience comes from flexibility.
It comes from flexibility and adaptation. It comes from materials that can heal themselves and structures that can move with the shock waves instead of shattering. We need to stop trying to be stronger than nature and start trying to be smarter.
Or at least as smart as Li Bing was in 256 BC.
That would be a very, very good start.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.